Okay, well, I don't know if anybody's going to show up, but welcome, Calc 1 CBE review for CBE number 5. My name is McCade.
I'm Ashley.
Just a couple things of note. This is recorded, so we are not recording faces. We're just recording the screen, basically. If you have any issues with that, please let us know afterwards. If you have any questions during or about the presentation, please let us know. Questions are great. Someone probably watching online will have them too. But if you have like any personal questions about what you're currently working on in your own homework or anything, we do ask to wait till afterwards, and we can answer those afterwards.
Yeah.
I think that's it. Yeah. Cool. So CBE 5 covers lessons 14 through 15. So that's L'Hopital's rule, indeterminate forms, antiderivatives, and then kind of some in-context antiderivative problems with initial values. So just a double check and with a review, a limit of a function is what the function approaches as x approaches the given value. So wherever the graph is approaching, as x approaches that value. Often found by plugging in the given value for x, but sometimes we have these cases where we can't just do that, so we got to do some manipulation, some other things first. Secondly, there is the theorem of if a limit exists on the right side, so as it approaches from the right, and as it approaches from the left, if those both exist, then the limit exists, and vice versa. If one approaches from the right, but doesn't approach the same spot from the left, we say that the limit does not exist. So this is just going to be a review problem. So determine the numerical value of this limit. So kind of first thing for any limit, I always just try to plug it in, see if it works out. If it doesn't work out, then we can see if we can do some stuff from there. So that's just going to be equal to 4 of -1 cubed plus 9 -1 squared minus 3 -1 plus 4 all over 3 times -1 squared plus 15 times -1 plus 14. It's a lot of negative ones. So we got, that is going to be equal to -1 times 4, so -4 plus 9 times 1, so that's plus 9, minus a -3, so that's plus 3, plus 4, all over, that's positive 3 plus a -15, so ignore that, that's a minus, 15 plus 14. Those four, oh, well, there's a spoiler alert. But that's going to be 12 over, that gives that's -1 plus 3, that's over 2, which is 6. Any questions on that? Awesome.
Sweet.
Alrighty. So then we're going to start going over L'Hopital's rule. And so this is when we're taking the derivative of a quotient, and if the limit of both the numerator and the denominator is equal to 0 over 0, or infinity over infinity, negative infinity over negative infinity, then the limit is equal to the derivative of the numerator divided by the derivative of the denominator. So we've kind of got a nice little visual here. And remember that the limit of the numerator and the limit of the denominator, they need to approach the same value, or else we'd have to use different limit properties. So if you guys notice, we're given this we're asked to find the numerical value of this limit. So it's limit as x approaches 3. If we were to just plug in our values for x like we did on the last problem, we'd have 2 times 3 squared plus 3 minus 21 all over 3 cubed minus 9 times 3. And you'll notice that this gives us, well, we have 3 squared is 9 times 2 is 18 plus 3 minus 21 over 27 minus 27. And that gives us a 0 over 0. So this means, okay, we're going to have to use L'Hopital's rule in order to find the limit. So we know that we'll notate this here with a little L over H, right? And we're going to take the derivative of the numerator first. So we have the limit as x approaches 3. And we'll take the derivative of the numerator. So if we multiply the 2 by 2, we get 4x plus the derivative of x is just 1. And that constant goes to 0. All over, and then we'll have 3 times x squared minus 9. Right? Then we can now plug in our limit as x goes towards 3. And this gives us 4 times 3 plus 1 all over 3 times 3 squared minus 9. And you'll note that this is equal to 4 times 3 is 12 plus 1 is 13 over 3 squared is 9 times 3 is 27 minus 9, which is 18. And we'll find that our solution is 13 over 18.
One thing that's fun about this one is technically we couldn't, or we didn't have to do L'Hopital's. We could have factored out an x on the bottom, done a difference of squares, factored out the top. Like an x minus 3 would have canceled on top and bottom and solved it that way. But L'Hopital still works. So.
Thank you.
Yeah.
Okay.
Oh, hello.
Sorry.
All right, you're good. Okay, so this, again, we got some sort of quotient. If we plug this in, this ends up being 4 to the 0 minus 2 to the 0 over 5 times 0. Do you guys know what any power to the 0th power is? 1. So that's going to be 1 minus 1 over 0, 0 over 0. So again, we need to do L'Hopital's. I don't think there's going to be a fun, easy algebraic manipulation that we can do here. So we get, applying L'Hopital's, that's going to be the limit as x approaches 0 of the derivative of the top. Do you guys remember what the derivative of an exponent with a non-e base is? If you don't, that's okay. It's not one that comes up. When we were reviewing this the other day, I had to look it up. I had to look it up. So I'll just spoiler alert. That's going to be 4x. So the top state, or the kind of like e to the x, it stays the same, but then we have to multiply by ln of whatever the base is. So then minus 2x times ln of 2 all over derivative of the bottom is 5. Again, kind of when we were starting Calc 1, we did derivative of quotients. We did the quotient rule. Don't do the quotient rule when doing L'Hopital's. We need the derivative of the top. Separately, we need the derivative of the bottom. Two kind of separate ideas. So that's going to be equal. So that goes to 1. It's going to be 1 ln of 4 minus 1 ln of 2 over 5. Do you guys remember your log properties very well? How could we simplify the top?
Oh, they're minusing.
Mm-hmm.
So you can combine them all into 1, and it can just be 1 natural log of 4 divided by 2.
4 divided by 2. When you subtract logs, you can bring that inside and turn it into division. Conversely, if you add logs, you can turn it into multiplication just inside of the log. Over 5. Oh, sorry, that's supposed to be... No, okay, we're good. So that's going to be equal to ln of 2 over 5. 4 divided by 2 is 2. And I promise it says it down there. Okay.
Okay, so now we're going to talk about some indeterminate forms. So sometimes, like we said, if we don't have the 0 over 0 or the infinity over infinity, we run into some issues. So if we have the limit as x approaches a of f of x, and that's equal to 0, and then the limit as x approaches a of g of x, and that's equal to infinity, then the limit as x approaches infinity of f of x times j of x may or may not exist. What's 0 times infinity? It's kind of tricky, right? And similarly, if our limit as x approaches infinity of f of x is equal to infinity, and the limit as x approaches a of g of x is equal to infinity, then the limit of f of x minus g of x may or may not exist, right? One last indeterminate form is the limit as x approaches a of f of x raised to the power of g of x. And so that looks like, okay, if we have 0 raised to the 0, or if we have infinity raised to the 0, or 1 raised to the infinity, we do have to use some manipulation to figure these guys out. So we can use L'Hopital's rule, remember, only when we have a quotient of two functions. So for those first two indeterminate forms, we can usually rearrange those functions so that it becomes a quotient. And then once it is written as a quotient, we can use L'Hopital's rule to evaluate the limit. But for indeterminate forms of the form f of x raised to the power of g of x, we have to take the natural log of the function in order to be able to use L'Hopital's rule. So we'll take the natural log, we'll expand the exponent using log rules, then rewrite the exponent to be a quotient so that we can use L'Hopital's rule. And chug away, I guess. So we'll practice this on problem 4. And so we know that this can be set equal to y, right? We have y equals the limit as x approaches 0 from the right-hand side of 5x raised to the power of 3x. So what we can do here is we can actually take the natural log of both sides. That's going to leave us with the natural log of y being equal to the limit as x approaches 0 from the right of 3x times the natural log of 5x. Okay, so I took the natural log of both sides. That's what we get. And so now I have this function here that I want to convert to a quotient. And so what I'm going to do is I'm going to still have my limit as x approaches 0 from the right. And I'm going to put the natural log of 5x in the numerator and divide by 3x to the negative 1, right? So I can put that in the denominator by taking 3x to the negative 1. Okay, now I need to use L'Hopital's rule, so I'm going to take the derivative of both the numerator and the denominator. So if I take the derivative of the natural log of 5x, that's a chain rule problem. So I have 5 times 1 over 5x. And that will all be over. We have a negative 1. And we could put this over 3x squared. Okay. So we took the derivative of both the numerator and the denominator. And we know that this is equal to, if we simplify this a little bit, we have 5 times 1 over 5x. That leaves us just 1 over x. And we know that if we have a fraction divided by a fraction, then we can multiply by the reciprocal. And so that lets us do negative 3x squared over 1. And actually, I think I'm going to simplify this 3x squared here to being negative 9x squared. So I just distributed that squared, right? Which gives me negative 9 times x, okay? And if I take the limit of negative 9x, that is going to be equal to 0. So I have the natural log of y is equal to 0. So then if I raise this to the power of e, I would have y is equal to e to the 0, which is equal to 1. Okay. And that's our solution to that one.
Dang, I've always done a shortcut of that. I've never done it that way. Anyway, I've done it way similar.
That's fabulous. Please,
Yeah.
shortcuts are great.
Well, I just you do e to the ln of everything, and then you just manipulate the power.
Wait, that actually is fabulous.
And anyway.
Yeah.
But
Okay. Well,
anyway,
on this
yeah.
one. That's perfect.
So again, let's plug it in. So that's going to be 1 minus 0 is 5 over. But again, it's approaching 0. So basically, this guy is infinity. That's one of our indeterminate forms. You might be asking yourself, why is 1 to the power infinity? I thought 1 to any power was 1. Turns out that this can either equal 1 or e. And since it can technically equal two things due to some limits and some other stuff, we call it indeterminate. There we go. Let's do some L'Hopital's. So I'm going to do limit, if I can go back, thank you. Limit as x approaches 0 from plus is equal to, if we're trying to multiply by this ln, so we can do some ln manipulation, we can't just multiply by ln unless doing it on both sides, or we need to multiply by 1. Do something that equals out to 1. That being, e to any ln power is just whatever is inside of the ln. So that's what I'm going to do. E to the ln of 1 minus 7x over 3 to the 5x. Big parentheses. So now we got the limit. I'm going to skip the as x approaches just because I'm going to have to write it like 12 times. So keep that in mind. Of e to the ln of, we can pull that 5x out front and be left with 1 minus 7x over 3. That's supposed to be over x. But again, we need this as a quotient. So I'm actually going to do the reciprocal of that 5x and divide by it. So that's going to be limit of e to the ln of 1 minus 7x over 3 over x over 5. Now, this portion is in the form of L'Hopital's. We can now do L'Hopital's to this. So that's going to be equal to the limit of e to the derivative of the top. Derivative of an ln is, I'm forgetting, oh my gosh, negative 7 over 3. Oh, so derivative of the inside over whatever the inside was. 1 minus 7 over 3x divided by the derivative of the bottom, which is just 1/5. That looks terrible, by the way. That's just going to be equal to, dividing by that, move the reciprocal, that's 5 out front, times a negative 7/3 times over 1 minus 7/3 x, all to the power of e. I am now going to evaluate this limit. So that is the limit as x approaches 0 from the right-hand side. That is going to be equal to negative 35 over 3 over 1 minus, that's 7/3 times 0. So that's 1 minus 0, which is 0 to the power of e. And we are left with e to the negative 35 thirds, assuming that I did it right. Yep. Any questions on that? So both ways are viable. You can multiply by ln on both sides, set it to some number, and then once you get there, e to the ln on both sides, that get your answer. Or if you want a little bit of a shortcut, you can like skip that, setting it equal to e, etc., etc. It's whichever you prefer. Okay, antiderivatives. What is an antiderivative? An antiderivative of a function is where the of f is a function whose derivative is f. So it's just undoing a derivative. You ask yourself the question, okay, if I took a derivative and I got this, how did I get there? So the collection of all antiderivatives of a function is referred to as the indefinite integral of f with respect to x. We add an arbitrary constant plus c, because anytime we take a derivative and we have a constant on the side, that goes to 0. So there could be this mysterious constant out front. We just don't know what it is, because there's an infinite amount of possibilities. So we add on this plus c. Here are the most common antiderivative formulas. The ones I would like to point out are, you won't use this one very often, but you might want to note it. Bonk, bonk. Eventually, you might see a bunch of these. These that I'm not underlining are uncommon, but especially probably in Calc 2, you're going to see it at least once. But the underlined ones are the ones that like you're going to need for the test potentially. So I will say the negative version of this guy is the cosine inverse. So if you memorize the sine version, the negative version, so the 1 over root 1 minus x squared, that's your cosine inverse. So that's kind of interesting. Cool. So problem, or do you want to do this one? Okay.
Either one, I'm good.
Cool. Evaluate the integral of 8 over x root x plus 6 to the 4th root of x to the 5. Personal preference, I hate square roots. I hate looking at them. They're not fun. They, like, respectfully, they suck. So I want to make this look better. I'm gonna remember how a root or any sort of radical you can represent as an exponent. Kind of like how x squared, the inverse of that is obviously the square root. So in the powers, 2 divided by 2, that's x to the 1. They undid each other. So x to the 1/2, that's the radical power. So I'm going to simplify this into 8 over, so the integral of 8 over x times x to the 1/2 plus 6x to the 5/4. Again, the radical is the division, the power is, or the radical is the denominator, the power is the numerator. This simplifies into the integral of 8 of x to the 3/2 plus 6x to the 5/4. Again, personal preference. I also don't like dealing with powers in the denominator or variables in the denominator if I could help it. So I'm going to simplify this again into the integral of 8x to the negative 3/2 plus 6x to the 5/4. Okay, if we go back, we see that x to any n, where n is not -1. That can be a fraction n, that can be an integer n, etc., etc. We just need to up the power and divide by that new power. Kind of the opposite of multiplying by the previous power and then subtracting 1. So that's going to be equal to 8x to the negative 3/2 plus 1 divided by whatever negative to the 3/2 plus 1 is, plus 6x to the 5/4 plus 1 divided by whatever 5/4 plus 1 is. Now we got to do some simplification. Oh, can't forget it, plus c. Now I'm going to move over here. So that's going to be equal to 8x negative 3/2 plus 1. That's going to be negative 1/2 over negative 1/2 plus 6x 5/4. That's going to be 9/4 over 9/4. More simplification. You could leave it here, and I'm like 99.9% sure your software would recognize it for your CBEs. In case you're kind of a perfectionist, sometimes like I am, I'm going to change this into negative 16x to the negative 1/2 because we're dividing by a fraction or multiplying by its reciprocal, plus that's going to be 24 over 9 x to the 9/4 plus c. Apparently that simplifies.
Yeah.
That simplifies back down into a radical. Any questions? Cool.
Okay. So we're now going to evaluate this integral. Since we have two functions multiplied by each other, I'm going to FOIL this. So that will give us the integral. If we have 2 times x squared times 5x, that gives us 10x cubed. And then we have 2 times x squared times minus 1, so that's a negative 2x squared. Then we get a positive 15x minus 3 dx. Okay, so after FOILing, we are going to take the integral. So remember that if we are integrating in respect to a constant, we can pull out the constant. So we have 10 times, then we know that x cubed, we can multiply by 1/4 x to the 4th. So if I multiply, if I were to take the derivative of this, I have 4 times 1/4 x cubed, which gives us x cubed, which is what our original function was. Okay, and then we have negative 2 times 1/3 x cubed plus 15 times 1/2 x squared minus 3x plus c, our arbitrary constant. And then just simplifying this a little bit, we get 10 times 1/4. That will simplify down to 5/2, right? Times x to the 4th. And then that'll give us a negative 2/3 x cubed plus 15 halves x squared minus 3x plus c, which I believe is our answer here. Any questions on that one? We okay? Okay.
You were asking yourself a question of like, what if I didn't want to FOIL it out, or what if I didn't want to multiply through? You can technically do a thing that you'll learn in CBE 7 for that, but at least that one, I think it's 10 times easier. Multiply through, do the integral. Okay. Evaluate the integral of -5 sine of 3x plus 4e to the 2x. Okay, I'm going to go all the way back. We're doing this guy, and we're doing this guy. So, antiderivative of e to the x is just e to the x, kind of like how the derivative is just e to the x. And then sine, when doing the integral, goes to negative cosine. So, we have the integral of -5 sine of 3x plus 4e to the 2x dx. You might be asking yourself, sine of x isn't sine of 3x. How do I deal with this 3x? And then you can go, okay, we know that this is going to be some sort of negative cosine of some x with some probably like k out here that we're multiplying to get to this sign. If I were to take the derivative of this, whatever that k might be, doing the derivative of some x, potentially 3x, I would get k over 3 negative cosine of 3x. So, not negative cosine, k over 3 sine of 3x. There we go. That negative goes away. Trust.
Would it just be 3k? And then
It would be 3k. Oh my gosh, I'm blundering.
No, that's okay. We're good. It's like
3k, whatever it ends up being. So, I have this extra 3 out front. I don't have that extra 3 over here. To go back, I would have to divide by a 3. So, I'm just going to do that. To go back, because if I were just to take the derivative of this, I would get an extra 3. So, to go back, I need to divide by that potential extra 3 that could have been there. So, that's going to do -5 over 3. The negatives cancel. Hello. negatives cancel, and that's going to be cosine of 3x. That same kind of logic is going to apply to this e to the 2x. When I take the derivative of e to the 2x, a 2 comes out front. And I don't, or technically there is 2, but if this was a different example, that 2 wouldn't be there. So to go up, I would need to now divide by a 2. So that's going to be plus 4 over 2 e to the 2x plus c. How are we feeling about that? It takes a little mental gymnastics, but we do get there eventually. Got some head nods?
I think we're good.
Okay, awesome. And that'll simplify the 2. So, cool. Initial value problems. For initial value problems, we are given some derivative of a function with initial values, and then asked to find the original function at a point. So first we need to find the indefinite integral plus c, and then we take this initial value, we solve for c, and we end up getting whatever that original function used to be. So this kind of situation gets rid of that plus c. Yeah.
Okay, so for this initial value problem, I'm going to put a little comma right here to kind of separate because this is looking weird on this PowerPoint. Okay, so we're given 2 initial conditions, and then we're given our function here, right? And it's f double prime of x, right? So first thing I want to do is I want to find f prime of x, and the way I'm going to do this is I'm going to take the integral, right? So what I want to do to this is I want to take the integral of 6x plus 3 dx, okay? And once I do that, I find that f prime of x is equal to, okay, well, I know that this is going to become an x squared, so I'm going to get 6 times 1/2 x squared, right? Because if I were to take the derivative, we'd have 2 times x, and so we're wanting to get rid of that too. And then we'd have plus 3x plus c. So that's our f prime of x there. And then note that we have f prime of 0 right here, and we know that that's equal to 2. And so what we're going to do is we are going to plug in 0 into our f prime of x function to solve for c. And so we can do this by taking f prime of 0, which is equal to, if we were to multiply this out, oh, sorry guys, I didn't simplify this. Okay, this is equal to 3x squared plus 3x plus c. Okay, perfect. All right, so that gives me 3 times 0 squared plus 3 times 0 plus c, and that's equal to 2 from my initial condition right here, right? So then we know that this would give us, okay, well we know that 3 times 0 squared is 0, 3 times 0 is 0, so that just leaves me with c is equal to 2, right? So that means I can come over here, and this guy, we can actually fill in 3x plus 2, so we know that c is equal to 2, okay? So now, oh, there's my solution, okay. So now I want to find f of x. So what I'm going to do is I'm going to take the integral again of our new function here. And so we know that f of x is equal to the integral of 3x squared plus 3x plus 2 dx. So integrating here, I have 3 times, and then if this is going to be an x cubed, I need to multiply by a third, plus 3 times 1/2 x squared plus 2x plus, now I need a new constant, let's call it d because I already used c. Is that okay? Okay, and if I'm simplifying this guy, it's going to give me x cubed plus 3 halves x squared plus 2x plus d. Okay. So that is f of x. And I know for f of x, for f of 0, that's equal to 5. So let's go ahead and plug it in like we did before. So I'm going to come over here. I'm going to write f of 0 is equal to, I'm going to have a 0 cubed plus 3 halves times 0 squared plus 2 times 0 plus d is equal to 5, right? Because that was my initial condition. Okay. A lot of this simplifies down to 0, and that leaves me with d is equal to 5. So now I can come back over here. I know that d is going to be equal to 5. Oh no. Okay, and now our initial question was to find f of 2, and we already know f of x, so now we can just plug 2 in to f of x. So I have f of 2 is equal to 2 cubed plus 3 halves times 2 squared plus 2 times 2 plus 5, right? So I know that 2 cubed is 8 plus 3 halves times 4 plus 4 plus 5, which is equal to, I know that this guy is going to simplify down to 6, okay? So I have 8 plus 6 plus 4 plus 5, and that will be equal to 8 plus 6 is 14, plus 4 is 18, plus 5 is 23. And that was our solution there. Okay.
Can't tell, these problems take a little bit.
Yes.
Yeah.
Okay. Solve the initial value problem and find 5 pi. So we originally have f double prime of x is equal to 5 cosine of x minus 2 sine of x. Okay, so f prime of x is equal to the antiderivative of that. So if I do the integral 5 cosine x minus 2 sine of x, that is going to be, I'm going to draw my little thing. Sine goes to cosine goes to negative sine goes to negative cosine. You go down the list, that's derivatives. You go up the list, that's antiderivatives. So cosine goes to sine. It's going to be 5 sine x minus sine, negative sine goes to cosine. So plus 2 cosine x. Okay, plus c. My preference, I like to do a little c1. And then the next time you see a c, you do c2. Obviously, you can do c and d, etc., etc. So now I get f of 0 is equal to 1. So f prime of 0 is equal to 5 sine of 0 plus 2 cosine of 0 plus c. Sine at 0 is 0. And then cosine at 0 is 1. So sine, that cancels out, plus 2 times 1, which is 2, plus c is all equal to 1. I minus that 2 over. I get c1. Please. Thank you. Please. There we go. Technical difficulties. C1 is equal to negative 1. Any questions on that? Okay, now I got to plug that in. So we get f prime of x is now equal to 5 sine of x plus 2 cosine of x plus a negative 1. And I now want f of x. So that's going to be equal to the integral of that same thing. Just going to write it out, plus 2 cosine of x minus 1. That's going to be sine, goes all the way down, back down to negative cosine. So that's negative 5 cosine x. 2 cosine, that goes back to sine, plus 2 sine of x minus 1x plus c2. Now I got to solve for that. So that's going to be f of 0 is equal to negative cosine of x, negative 5 cosine, there we go, plus 2 sine of, 0, minus 1 times 0 plus c2. Cosine, I just said that was 1, so that's going to be negative 5 times 1, plus sine is 0, plus 0, minus 0, plus c2. It's all equal to, where is it? 4. 4. So add 5 over, leave c2. That's going to be c2 is equal to 9. So now 5, or f of x, is equal to negative 5 cosine x plus 2 sine of x minus 1x plus 9. So that f of pi, cosine, that's sine. Sine goes to 0, cosine goes to negative 1, so that's going to be negative 5 times 1, so 5 plus 0 minus 1 pi plus 9, and we will get 14 minus pi. And boom. Sorry, my handwriting's a little bigger. Kind of took up the whole page.
That's great.
Okay, how are we feeling about that?
It's all good. It's just a lot.
Cool. Yeah, it is a lot.
New, but sounds good.
When I was recitation leader for this back 2 falls ago, my number 1 tip: 1, go slow. I guess 2 tips. 1, go slow. 2, organize your information.
Yeah.
If I had more space, I would have put f double prime up here, f prime, f not, whatever C1 end up being, C2 being. You have it multiple places to where you can't get mixed up. That's my biggest suggestion, especially for questions that take, how many steps did we just do? 20? So, too many. So, okay. So that's the end of the presentation. Other resources, of course, we have got the Aggie Math Learning Center. That's next door, room 118 of the Animal Science Building. Secondly, this will eventually, within week-ish,
It'll be there.
it'll be on the
I'll do it on
YouTube.
Monday.
It'll be on the YouTube page, so you can look that up, Aggie Math Learning Center, or you can go to our website that can link you there. There is currently a video from last year there, or last semester. We re-update them every semester. So if you want to do some different examples, that's very similar structure, you can look there. So, cool.